Yeah, so now we are recording, and we are starting to consider the topic of discrete, actually not only discrete, but further, finally we will go to discrete wavelet transform. So our topic for today, the discipline theory of signal processing, is a wavelet transform. And I'm starting my share my screen. Do you see it, Ahmed?
Yes, Dr.
Is it okay, or should I enlarge the?
No, it's great. It's great. Yes.
So discrete wavelet transform. So
Transform, yes.
the new, a little bit strange word, wavelet, but I will try to explain. Okay, let's start. So the wavelet, it's like a word that could be divided into parts. The first one is wave, like a pulse, yes?
Yes.
And the let is like something small, yeah? So together, when these parts are combined together, so we will obtain wavelet like a small wave. And this term reflects the idea of wavelet analysis. So the basic function of this method is really very small oscillation or small wave, like, for example, here in the slide that you can see. So it's a small located waves that are considered like a basic function. So we will analyze the original function, the original signal, using this basic function as a small waves. And also we will use two main operations. One of them is scaling. What does it mean, scaling? We just enlarge or decrease the function, this basic function. So we will consider it like in different scales. It means that due to this method, due to this analysis, it is like an instrument how to analyze the function at different scales in order to be able both consider the very small details in the function, but also to consider a function at whole and consider its behavior. So it's like a multi-tool instrument that allows us to, that gives us more possibilities in comparison with traditional spectral transforms that we considered before. So here there is different variations and different possibilities for consideration, for investigating the original function at different scales. That's why it is called multiple scale analysis. So we analyze the function using different scales. And actually, I will not stop on these words. It's a little bit boring, but we will see more to the practice. As for any traditional method, like Fourier and whatever that we considered, and also for that we didn't consider, there are two ways how to analyze the function. Actually, not two ways, but two directions. So we have original function that we would like to analyze. Then we are applying some method, and actually we are doing direct transform. And as a result of this transform, in case of Fourier or other spectral method, we obtain a spectrum. And also we can return back for the known spectrum to calculate original function, so to return back our original signal. But in case of wavelet, this procedure is a little bit different. Actually, there is, I would say, not complicated, but it is more different because we have a couple steps on the way from original function when we are starting analyzing it. So anyway, we are doing decomposition. It means that we just taking original function and decompose it into different components. So it is direct transform like for Fourier, because Fourier it's like our example, our golden standard, and we are just comparing all the time as a method that we're considering with the golden standard of Fourier. So here in Wavelet transform we have direct transform. When we it is also, we could say that it is an analysis of function. So direct transform, it's the same like analysis. It's another word for the direct transform. And also the third word that reflects the same process is a decomposition. So the direct transform is analysis and decomposition. The inverse operation is a synthesis. So the opposite thing to the analysis is synthesis. So after we do this, we did this decomposition. So we have a couple components as a result, and at the way back, we just collect all these components and we do synthesis of function, or in other words, we are doing reconstruction of the function. So we reconstruct the original signal. And in traditional wavelet, during this decomposition stage, we are using two filters, like a low frequency and high frequency component. So initial signal, original signal that we are going to analyze, we are just splitting it into two components. It's like a two data stream for low frequency component and high frequency component. But the interesting thing is that we are doing the same, not only once, we are doing it at different steps, and amount of the steps could be quite a lot, quite a big. And this amount actually depends on how many digits do we have in original function. At each step of decomposition, we are doing this splitting using two filters, low frequency and high frequency. And as a result, at each step, we obtain two components. One of these components is a low frequency component. So it will be like approximated version or smoothed version of initial signal. And the second one will be a high frequency component that represents the oscillation around this first component. So the first component, it's like a common behavior of original signal without oscillation. And the second one, it's oscillations themselves. So first one is called the noise, the trend. So the smoothed version of original function. When we take out all the high frequencies, we obtain this smoothed version, and it is called a trend. And a high frequency component, there are an oscillation around this trend, or it also could be called noises. So trend and noises. At the next step, we are taking just a trend, not noises. We are taking just a trend from previous step, and we again splitting it into two components, low frequency and high frequency. And as a result, we obtain a new trend that is more smooth, like a previous one. So this is like an idea. I will show it later, because in some slide we will have a like a flow chart of how it works. But also important thing that at each level of decomposition, now we know that it could be different levels of decomposition. So at each level, we have one scaling function that is responsible for the scaling, because scaling is one of two main operations in a wavelet analysis. And the second one is a parent wavelet. And actually this second function, a parent wavelet, is responsible for the basic function itself. So when we are taking this or that function and consider it like a parent wavelet, we will obtain a different methods, like a different methods was Fourier, Hartley, Walsh, and other function. Oh, some error. Just a second, I don't know why, but I was switched out from my account, so I have to open it again. Yeah, at least, and then we will find the proper slide. If you have some question, you can interrupt me in any time and ask. Okay, so here, starting from the slide number 4, it becomes more interesting because now we are starting considering concrete wavelet that is the simplest, the most simple that could be imagined. It's called Haar wavelet. So Haar, it's the name of this wavelet. Actually, this is the name of the mathematician, but also there is a name of the most simple discrete wavelet that could be imagined. Each wavelet could be described by two functions, as I told you before. Its first one is a scaling function, and second is a parent wavelet. So for Haar wavelet, Haar, we have first function that is very, very simple. It is equal to 1 at the interval that is also has a duration 1. And it is noted by the Greek letter phi from x. So this first function, you can see it here on the graph, but also you can see it here on the, like in form of equation. So it is the scaling function, and this scaling function is always the same. So for any wavelet, the scaling function will be the same. It will be a function that is equal to 1 at the unitary interval. But the second function will be different for different wavelets. So in our case, in case of Haar wavelet, we will use this function that is also called Haar wavelet. Actually, this is like a second, like in previous slide, a parent wavelet. So parent wavelet for the Haar method, it is like here. So this is a function that is marked by Greek letter psi from x here. And this function is equal to +1 on the first half on interval and -1 on the second part. Here there is a graph, and here there is a formula for this parent wavelet of Haar. But also for these two functions, we will use both of them at each step, at each level of decomposition. So we will do a decomposition. This decomposition will include couple levels, couple steps. And at each step, we will apply for the scaling function phi and for the parent wavelet psi, we will apply two operations. First one is a scaling, and scaling means changing of scale, and this changing could be in horizontal direction, but also in vertical, so in both directions. So both this function phi and psi will be the object of a scaling on horizontal and a vertical direction, and also shifting. Shifting means the movement across the horizontal axis. And these two operations that are the main operations at wavelet method is reflected by these equations. These two equations, I'm sorry, I would like to do it a little bit more, but I think now it's okay. So this two equations, you could mark that they are very similar. The only difference between them is these two Greek letters. It's phi and psi. So the phi is a scaling function and psi is a parent wavelet of Haar. And also we are using here two variables. First one is J and second one is K. So these two variables, we will consider them like a two counters. First counter that is marked at J is a number of the level of the composition, and this number will be changed from the maximum value, so it will be decreased till 0. A little bit later, I will explain how to define what is the maximum value. But anyway, this number of the level will change from the maximum value till 0. And here, how to understand what is maximum. J maximum is equal to n, but what is it n? How to obtain it? Let's take a look a little bit above here, and there is an interval, because we are dealing with the discrete method, so the n capital is the number of discrete values of original function. As for example, in your practical work, you had let's say practical task number 2, it was a discrete Fourier transform, and in your variant you did have 5 values, so your n was equal to 5. This is the amount of values that is assigned by original function. So here in this method, in the method of Haar wavelet, it is necessary to have original function that is defined by n values. And you can see that there is very important condition that this n should be like a power of 2. So it is no more allowed, like it was in Fourier transform, that it could be arbitrary number of discrete values. Here in Haar wavelet, it is necessary to have original function that has 2 in the power n values. So it could be 4, 8, 16, 32, and so on and so on. So it could be as big as you need, but anyway, it should be a power of 2. It's very important. So if you don't have it, if you have another amount of digits at original signal, you have to do something before in order to be able to apply wavelet transform. So initially you have to count all your values and to be sure that this number is 2 in the power n. If not, you have to do something, maybe to remove some amount of digits, or maybe to do something else, but you have to provide n equal to 2 in the power n. Only after this, only if you provide this condition, you could be able to apply wavelet. So this is very important. And when you are already successful in this, so if you have already 2 in the power n discrete values at original function, okay, very good. The first step is done. Then we just should have a look to this power of 2. So which power do we have? If we have 4 values, so which power we'll have in this case, Ahmed? For example, n equal to 4.
N equal to 4, it will be 2.
2 in the power 2. But
yes.
If it will be not 4, but 1024, what will be the power?
N equal 1024.
1024. Which power of 2 it is?
1 second.
Not so easy, yeah?
Yeah.
Okay, let's go 2 in the power 3. Let's go from the simple. 2 in the power 3 is equal to what?
2 in the power 3, it will be 9.
Not 9.
2 is capital, yes? And
2 in the power 3 It means 2, you should multiply 2 by itself.
8.
8, of course.
Yes.
If we will have 16, which power it is?
16.
Mhm.
It will be 4.
4, of course. Then 32.
32. It will be 6.
Not
No,
6.
no.
16 was 4, so 32
6.
is okay. 32 is 2 in the power 5.
32.
32 is 2 in the power 5. And also you can enlarge it, of course. And if you have 1024, it means 2 in the power 10. So that's just an example in order to understand that the second step after you became sure that you have a proper number of values, so it is 2 in the power n, then you have to indicate what is this power, which is this number. Is it a 2 or 3 or 4 or 10 or more? Because it is like a starting point from your decomposition. When you know this power, it means that you know automatically the maximum level of decomposition. So if you have 8 values, 8 is 2 in the power 3, it means that your maximum level, J maximum, equal to 3. And if you have 1024, that is 2 in the power 10, it automatically means that maximum level of decomposition in your wavelets will be 10, 2 in the power 10. So this power of 2, it's like a starting point from the counting of the level of decomposition. So level of decomposition is defined by the counter J, and this counter is changes its value from the maximum value till 0. So J maximum equal to n. That could be different depending on your concrete example. And then it starts decreasing. J maximum, then J maximum minus 1, then J maximum minus 2, and so on till 0. When it reaches 0, it means that you just finished. You cannot do more decomposition. You already have to the final point. But the question, not the question, but the idea is that it is not necessary, and in not all tasks it is necessary to go to the zeros level. You can stop at any level somewhere in between J maximum and 0. So you can do a one level, one step of decomposition, 2 steps, 3 steps maybe. So you are free to stop anywhere on this way. It is not necessary. It depends on the task, but I will explain it later also. Now we should just understand and remember that J, it's like a counter of the levels of decomposition, and this counters decreases each time, so the levels of decomposition will change from maximum value till 0. The next variable is K. And this K is a second counter that will be used during the wavelet decomposition. And this K will be considered like an internal counter. So inside each level of decomposition, we will have different values of K. So K will take all its values inside the concrete fixed level of decomposition. So for the concrete J, we will have a set of values K. for the next level, for the next value of j, we will have another set of k. So it will be like an external counter j and an internal counter k. And k is dependent on j. Using this equation, you could understand this. So k is changing from 0, 0, 1, 2, it is increasing till the maximum value 2 in the power j minus 1. So for the concrete fixed j level of decomposition, we will have some values of k. When we are going to the next level of decomposition, so the k started again increased from 0. And at each level, depending on the number of this level, we will have a different set of the values k. So, for example, if j is equal to 2, j equal to 2, then k will be changed as 0, 1, and 2 in the power 2 minus 1. 2 in the power 2 is 4. So 4 minus 1 is 3. So k will take a values 0, 1, 2, and 3. So totally 4 values. But if then j, like a level of decomposition, will decrease by 1, so will be decremented, and becomes equal not 2 but 1, then we should put 1 here. And at that level, when j equal to 1, our k will be changed till the value at 2 in the power 1 minus 1. It will be 1. So at that level, k will take only 2 values, 0 and 1. And at least at the last level of decomposition, where j equal to 0, we will put it 0 here. Instead, j and 2 in the power 0 is equal to 1, and 1 minus 1 is equal to 0. So k will be only equal to 0. That's all. So the main thing is that we have these two counters, j like a counter of levels and like an external counter, and k like an internal counter inside each level. It could be maybe a little bit difficult for understanding, but further in this presentation will be a concrete, very simple example, and I hope everything becomes clear because it's always more simple to understand how this or that mathematical method works by using the concrete example. So we will do it definitely here also. But before we will do it, we have to just to put all necessary ideas and formulas and just to give some explanation about this. Okay, so as I said, at wavelet decomposition, we have a couple levels of decomposition. And at each level of decomposition, only one exception, but a little bit later about it, at each level of decomposition, we will have two data streams or two components. Like I said, a low frequency component or the trend. And the second one is a high frequency component or oscillation around the trend. So high frequency oscillation. In order to describe these two components in mathematical way, we will use a notation for the two groups of coefficients. They are called wavelet coefficients. First group is a coefficient that will be marked by the letter S. So S is a coefficient that are describing approximation or low frequency or trend. The second group will be marked by the letter D, and these coefficients will describe the detailization, the noise high frequency oscillation around the trend. I said at each level of decomposition we have these both two groups, but the exception is the maximum level of decomposition. So when we are just at the start and we have only original function, and we are at the maximum possible decomposition level, J maximum. So at this maximum level, only at this level, this is only one exception, we have only S coefficients. We don't have a D coefficient, don't have a detailization. Only approximation coefficients. And here at the slide, you can see a formula of how to calculate these S coefficients at the maximum level of decomposition. And you can see that in the numerator of this formula, in the upper part, we have only values of original function, because our J is the original signal that we are going to analyze. So just taking this signal and doing some not complicated calculation with this, we obtain S coefficients for the maximum decomposition level. And that's all that we do at this level. So we have just to calculate this set of these S coefficients. For all other levels, we will calculate not only S, but also D coefficient. So approximation and detailization. And then after we did all the calculation at the maximum level, so we calculated S coefficients, we are going next to the next level, and we will use this coefficient that was calculated before at the previous level in order to calculate coefficients at this next level. So in any step at every level of decomposition, we will use S coefficients from previous level in order to calculate both S and D coefficients for the next level. So this is like a recurrent formulas that is proper for every level except maximum, because at maximum level we calculated only S. Here we can see in the right part of these two equations, we have the same Sj. This Sj, it's like a vector column. You can see it here a little bit below. And this vector column contains the S coefficients, just a pair of S coefficients, two of them, from the level J. S with the lower index J. And in the left part of these two formulas, we have S or D with the lower index J minus 1. So it means that we are already going down to the next level, to the level J minus 1. So in the right part, we use the coefficient from J level, and in the left part, we obtain, using this coefficient from the J level, from the previous level, we obtain the coefficients from the next level. This is like a recurrent formulas. Again, when we will come to the example, it will become more clear. And also very important thing, I told you that actually no need to go through all the levels of decomposition till zeros level. No need. It depends on the task. Sometimes it is necessary, but sometimes not. Maybe the task could be that, for example, we have some original function that consists of many digital values. And these values are just some different, yeah. So if we just put it on a graph, we will obtain something non-stationary, non-analytical. We could not describe it by some analytical expression or whatever. But if we will apply wavelet transform, and if we will, for this in wavelet transform, we will make some levels of decomposition. So at each level, we will obtain more and more smoothed version of initial signal. And maybe this smoothed version will be more suitable for the analysis and maybe for the prediction of how the function will behave in the future. So in such formulation, this task could be very interesting and promising. And actually, wavelet transform in many cases is applied actually for this aim, just for smoothing the original function and also the number of discrete values will be decreased, so it's more suitable and more simple to deal not with the original function but with its smoothed version. And going through the levels of decomposition, we will obtain more and more smoothed version. So it's our solution. It's up to us where to stop at this way and which degree of smoothing we will take for the analysis, for the prediction maybe, or maybe for some other operation. But anyway, very important thing that it doesn't matter how many levels of decomposition we do, we can stop at every of them in absolutely any level, and from this point, this or that, so we can stop in different points, but from every point we are able to go back to original function and to obtain it from any points of our decomposition. It's like an inverse transform, but here we have not only one inverse transform like it was in Fourier, in Hartley, in Walsh and Hadamard transform. Here we have a way how to come back from different points of decomposition. And this is like inverse transform, and it is called, in terms of wavelet analysis, it's called reconstruction of original function, like inverse transform. And we can do it from the highest level, from the next level, and actually finally from the last zeros level. So if we are just stopped after one level of decomposition. So we just at the highest level, and we calculated for this highest level only S coefficients. Then also we can use these coefficients in order to restore, to reconstruct the original function. Original function is marked as y from x. So here there is a formula for the reconstruction of this original function if we stopped at the highest level. So we have only these S coefficients, and as you can see, we should multiply each of these coefficients S by scaling function phi, because phi is a notation for the scaling function. If we didn't stop at this maximum level and just go further, then we can stop at the next level. It's a level when we calculated not only S, but also D coefficients, because I told you that two types of coefficients are calculated at each level except maximum one. So after one step of wavelet decomposition, we also could restore original function. And here there is a formula of how to do it. In this formula, we also have not only S, but D coefficients too. And at least if we didn't stop at each intermediate level and just we did our decomposition at the maximum possible number of levels, and we just came to the lowest level that is equal to 0, we also can restore original function. In order to do this, we have to take all the coefficients D that we calculated before and all previous steps, and also S coefficients that we calculated here at the zeros level. So we have, in order to restore, to reconstruct the function, we have just to collect all the coefficients that we calculated before at the previous level. And they will be helpful us to reconstruct the function in its original form. And here at least examples. So let's start to understand it better, how all this mathematical formula work. And as usual, example will be very, very simple because it's very important to understand everything in detail. So that's why we will take a very simple example and we will just consider it very carefully and in very details. Original function that we will consider here is our y from x that contains, as you can see, only 4 values. Only 4. These values are here in example 0, 1, 2, and 3. But in your case, it could be different. So it could be any numbers, positive, negative, integer, simple, so whatever. Not imaginary, of course, not complex values, real numbers, because this is original function. So if there is something like a result of the measuring or a result of calculation, so it is like values of some physical parameter. In our case, it's very simple, 4 values, 0, 1, 2, and 3. So we have 4, we have you remember I told you that the first thing that you have to do is just to count how many values do we have. Here we have 4. And also you should be sure that this number is the power of 2. So 2 in the power something. Here we have 4, and of course we know that 4 is, is 2 in the power, just a second, yeah, it's 2 in the power 2, right? So if you have 4, you know that there is a second power of 2. And it means automatically that your maximum possible level of decomposition, the starting point of your decomposition by wavelet, will be level your J maximum equal to 2. You are starting from J equal to 2. And this counter of levels, J, could be only decreased, not increased, but it is always decreased till 0. So in this very, very simple example, we are starting from 2, and J automatically takes the value at 2, 1, and 0. It is very important to understand it, because if you understand it for very simple example, you will be able to do it for the far more complicated cases. But now it is necessary to understand everything, every letter and every equation that would be here. So we have original function. We know that this function contains 4 values. It is automatically means that we know maximum level of decomposition, it is equal to 2, and also the possible levels that could be theoretically, and we will do all these levels, will be 2, 1, and 0. Our task is to find wavelet coefficients, Haar wavelet coefficients. It means that we have to use Haar wavelet that we considered right before for each of this level. So to calculate all possible coefficients of Haar wavelet for all possible levels of decomposition, for second, for first, and for zeros, and also to show how the function could be reconstructed. So we should find the reconstructed original function for each level. And now let's start. Of course, we are starting from the maximum level of decomposition. In our case, in our example, it is equal to 2. So J maximum level is equal to 2. And we are starting from this level. We know that for Haar wavelet, is not so good. For hard wavelet, at maximum level of decomposition, only at maximum level, we have to calculate only S coefficients, not D, only S. For all other, we will calculate S and D, two types of coefficients, but for the maximum, only S. Okay, here is the formula of how to do this. How to calculate these coefficients S. As you can see, each of these coefficients has two lower indices. First one is J and the second one is K. That's why I explained you the meaning of these two values. This is like two counters. J is a counter that indicates the number of the level. In our case here, it is equal to 2. And the second index K is like an internal counter that depends on J. So depending of the value at J, we will calculate of a maximum value of K. Here you can see it here. So K is changing from 0 till 2 in the power 2 minus 1. This power 2 appears because we are at the second level. So here this is the number of the level. So K will take values from 0 till 2 in the power 2 minus 1 means 0, 1, 2, and 3, totally 4 levels. And this formula already it is replaced. J maximum is replaced by 2. So we have S2, comma, K. And it is depending on the value of original function that is that we have from our example, from y from x. So it will be y from k over 2 in the power 2, and in denominator we have 2 in the power 2 over 2 again. Actually, the one more important thing that doesn't matter how much digital values do we have at original function. In any way, we have to represent all this value at the interval with the duration 1. If we have, for example, 4 values like here, so we are just putting them inside the interval 1. If we would have it 1024, for example, so anyway, we have to put them together inside the interval 1. So the question is to how many parts will be inside this interval. If we have 4 values, so it will be a quarters. If we will have 8, it will be a part 1 over 8. If we have 1024, so we should divide our interval into 1024 sub-intervals. So it is important to put them all together inside the interval with the duration 1. So like here, our 4 values will be put here. So the first quarter function is equal to 0, the second quarter 1, third quarter 2, and the last quarter equal to 3. This is our original function. And this is a formula of how to calculate S. So we should combine them together and put these 4 values of original function, here this value 0, 1, 2, and 3, into the formula for the S coefficient. And we will put K equal to 0, then 1, then 2, and then 3. And in the result, we will obtain 4 S coefficients. So for K equal to 0, we will obtain S2, 0. For K equal to 1, S2, 1. For K equal to 2, S2, 2. And for K equal to 3, the coefficient S2, 3. And in order to calculate first of them, S2, 0, we will obtain the first value of original function. Y from 0 is equal to 0, and the first coefficient equal to 0. To calculate the second one, we will take the next value, y from 1 over 4. So it means the value for the next quarter of the interval. This is the value number 2, it's equal to 1. So we have 1 in numerator and 2 in denominator. So our second coefficient will be equal to 1/2, 1/2. Then we are taking the next value, it's equal to 2. So 2/2 is equal to 1. And the last one, last value, 3. 3/2 equal to 3/2, of course. So here there is the end of calculation of S coefficients at maximum level of decomposition. And actually, that's all that we can calculate here. Nothing more. D coefficients are absent here, only at maximum level. All S coefficients we already calculated, so we are ready just to go further to the next level, or just to reconstruct original function if we would like to turn back. But according to the condition of our example, we need to come back. We have to show how it works for every how to return from every step of the composition. So the next step will be also to return back, and then we will show how to go further to the next level. But I think maybe it would be enough for today, because it's not a simple theory. I understand it clearly. I just would ask you just try to understand everything. If you don't understand, we could repeat it, and I'm ready to give you more explanation, because it's very important for you to understand it very clearly. Without this, you will not be able to apply this method and to just to solve a task and so on. But this method, once more, I repeat, it could be very interesting even for your own research. Maybe you will have some interesting task about the signal processing and so on. That's why I would like to give you this knowledge. Okay, so now I'm stopping at this slide number 9, and then we will continue next time. I'm stopping sharing my screen, and yeah, okay. Do you have some question, Ahmed?
No, Dr. Atila, it's okay.
Okay, is it complicated how you could?
No, not complicated. I think.
Okay, let's see how. Let's see how you will do it by yourself, and that you will see. Okay, so thank you very much for the attention. Have a nice evening and good luck.
Okay, good evening, Dr. Good evening.
Bye. Okay.
Bye.